There is something deeply suspicious about warm hands. Seriously. Think about it. You rub your palms together on a cold morning and suddenly heat appears out of nowhere. No fire. No glowing coal. No tiny dragon hiding between your fingers doing freelance blacksmith work, just motion somehow turning into warmth. Which sounds normal to us now, but for most of human history, this was borderline sorcery. And that's the strange thing about civilization. People can build empires long before they understand what they're actually doing. Humanity domesticated fire thousands of years before it understood energy. We cooked food, forged swords, powered factories, and launched industrial revolutions while fundamentally misunderstanding one of the most important processes in the universe. That's not an exaggeration. For centuries, many scientists genuinely believed heat was a physical substance, an invisible fluid called caloric. According to this idea, hot objects contained more caloric fluid, while cold objects had less. Heat flowed from one body to another, the same way water pours downhill. Which, to be fair, kind of makes intuitive sense. You touch a hot pan, heat moves into your hand. Ice cools a drink. Because coldness seems to spread, the theory felt elegant. Nor can I, unfortunately. Reality has a habit of humiliating elegant ideas because there was one horrifying problem nobody could explain: friction. Why does rubbing objects together create heat? If heat were literally a material substance, where was the extra caloric coming from? Were surfaces secretly leaking invisible thermal juice every time they scraped against each other? That explanation became increasingly ridiculous once the Industrial Revolution arrived and humanity started building gigantic machines designed to violently grind reality into motion. Steam engines changed everything. Suddenly, entire economies depended on heat. Coal became geopolitical power in rock form. Factories multiplied, railroads expanded, nations industrialized at terrifying speed. And everywhere across Europe, giant metal engines converted fire into movement through mechanisms nobody completely understood, which is exactly as safe as it sounds. Boilers exploded constantly. Factories burned. Engines wasted absurd amounts of fuel. Entire industries were operating like cavemen who accidentally discovered advanced machinery, but skipped the instruction manual. And underneath all of it lurked a deeper mystery. What actually is heat? Not metaphorically, not poetically, physically, because something profoundly strange was happening inside these machines. Heat could produce motion, but motion could also produce heat. A steam engine transformed fire into mechanical movement. Meanwhile, friction inside the engine transformed movement back into heat again. It looked less like separate phenomena and more like some hidden exchange system operating underneath reality itself. Almost like nature was converting one invisible quantity into another, but according to the old caloric theory, this made no sense at all. You weren't supposed to generate endless heat from motion, and yet blacksmiths did it constantly. Cannons heated during drilling, metal glowed under repeated hammer strikes. Wheels became hot after long travel. The universe kept violating the theory in broad daylight. And the truly unsettling part? Nobody knew where the energy bookkeeping was happening. Imagine trying to run a global financial system without understanding accounting. Money appears here, disappears there, moves through invisible channels nobody can track. That was thermodynamics before the 19th century. Civilization was operating a planetary scale energy economy using vibes, optimism, and occasional explosions. Not ideal, but then a few stubborn people began asking dangerous questions. Questions so fundamental they would eventually reshape physics, engineering, industry, and humanity's understanding of reality itself. Questions that would lead to one of the most important realizations ever discovered. The universe does not lose track of energy, ever. In the late 18th century, an American-born physicist working for the Bavarian military watched people drill cannons for hours, and what he noticed should not have happened. The man's name was Count Rumford, although history had already turned his biography into something that sounds partially fabricated. Spy, soldier, political survivor, scientist. The kind of person who feels less like a researcher and more like someone accidentally wandering through several genres at once. But during cannon production, Rumford encountered a problem that quietly detonated centuries of scientific belief. The metal cannons became extremely hot during boring operations. That alone was unsurprising. Friction obviously produced warmth. The disturbing part was this: the heat never seemed to run out. According to caloric theory, heat was a substance stored inside matter. So, if friction merely released trapped caloric fluid, there should have been a limit. At some point, the metal should become exhausted, like squeezing water from a sponge until nothing remains. Instead, Rumford observed apparently endless heat generation. The more drilling, the more heat, again and again. As though motion itself was manufacturing thermal energy, which was scientific heresy at the time, Rumford pushed the absurdity further. He submerged a cannon barrel in water during boring operations. The water eventually boiled. That experiment was deeply uncomfortable for the scientific establishment because it implied something horrifying. Heat might not be a material substance at all. It might be connected to motion itself. Now, this is where history becomes wonderfully human, because science does not progress like a clean documentary montage with inspirational music and immediate consensus. Scientists are people, which means they are tribal, stubborn, emotional, territorial, and occasionally capable of defending incorrect ideas with astonishing confidence. The caloric theory had prestige, textbooks, reputation, intellectual inertia, and intellectual inertia is one of the strongest forces in the universe. Slightly below gravity, slightly above internet arguments. So even after Rumford's observations, many researchers resisted the implications, but reality kept applying pressure. Because the 19th century was becoming an age of engines, coal-powered nations. Factories became economic weapons. Steam locomotives compressed geography itself, turning week-long travel into days. Industrial power determined military power. Engineering efficiency became geopolitical survival. And hidden underneath all this industrial chaos was a terrifying practical question: how much useful work can heat actually produce? That question obsessed a young French engineer named Sadi Carnot. Carnot was trying to understand steam engines, but not merely as machines. He wanted to understand their theoretical limits. Why were engines so inefficient? Why did so much energy disappear uselessly into the environment? At the time, nobody fully understood. Imagine designing aircraft before understanding aerodynamics. That was essentially industrial thermodynamics in its early form. Humanity had constructed civilization-scale machinery before discovering the governing equations underneath it. Carnot approached the problem with eerie elegance. He realized heat naturally flows from hot regions to cold regions, and engines exploit that flow the way watermills exploit falling water. A steam engine was not creating motion from nothing. It was channeling energy transfer across temperature differences. That insight was revolutionary, but even Carnot still worked partially within caloric thinking. The full picture remained incomplete. Then came James Prescott Joule. And Joule was relentless. If Rumford cracked the wall, Joule attacked the foundation with industrial-grade obsession. He performed experiment after experiment, attempting to measure the relationship between mechanical work and heat. One of his most famous setups looked deceptively simple. Falling weights rotated paddles inside water. As the paddles churned, the water temperature increased. Motion became heat, not metaphorically, quantifiably. And Joule kept measuring. Again, different systems, different materials, different conditions. He was hunting a conversion ratio hidden inside reality itself, a universal exchange rate between mechanical work and thermal energy. Which sounds obvious now only because modern physics has completely rewired our intuition. At the time, this was radical, dangerous. Even Joule was effectively claiming that heat and work were different manifestations of the same conserved quantity. Energy, that word would eventually become foundational to physics, but during Joule's era, the concept lacked the clean, formal structure we take for granted today, and many established scientists dismissed him. Partly because his ideas challenged existing theory, partly because science, unfortunately, contains humans. Joule wasn't some aristocratic academic celebrity operating from elite intellectual circles. He was connected to brewing industry work and practical experimentation. To certain scientific elites, his research probably felt annoyingly mechanical, too empirical, too hands-on. Which is ironic because reality itself tends to be extremely empirical. The experiments kept working, mechanical effort consistently transformed into predictable thermal change. The universe was exposing its accounting system. Eventually, physicists like Rudolf Clausius helped formalize these insights into what became the first law of thermodynamics. The realization was profound. Heat was not a mysterious fluid. Work was not fundamentally separate from thermal behavior. Instead, both were methods of transferring energy into or out of systems, and hidden beneath all visible processes existed something deeper. Internal energy, an invisible, microscopic reservoir inside matter itself. That idea changed civilization. Because once humanity understood energy conservation, engines stopped being mystical fire machines and became solvable engineering systems. Suddenly, efficiency could be calculated, power plants could be optimized. Industrial processes could be predicted. The age of thermodynamics had begun, and humanity was finally starting to realize something unsettling. The universe keeps perfect records. At first glance, the first law of thermodynamics looks disappointingly small, just a compact line of symbols, delta U a plus Q, which is unfortunate because humanity has a terrible habit of underestimating compact equations. Tiny equations routinely destroy civilizations' worth of assumptions, and this one fundamentally changed how we understand reality itself. Because hidden inside these symbols is a claim so radical, it took humanity thousands of years to fully articulate energy never simply disappears. Not in engines, not in explosions, not in your body, not in stars, not even when reality looks chaotic. The universe is apparently running the strictest accounting department imaginable. So let's decode the equation carefully, not like a classroom lecture. More like forensic investigators trying to uncover how nature secretly moves energy around behind the scenes. The first term is internal energy. Delta U, that innocent-looking symbol, represents something almost absurdly enormous. Every object around you contains invisible microscopic motion. Molecules vibrating, atoms colliding. Electrons interacting, entire storms of motion hidden beneath apparently calm surfaces. A cup of coffee sitting quietly on a table looks peaceful. It is not peaceful. It is molecular violence at reduced scale. Its particles are vibrating continuously in random directions like an overcrowded stadium after somebody announced free food near the exits. Temperature is basically a measurement of this microscopic chaos. The hotter an object becomes, the more intense the internal motion becomes. And internal energy refers to the total hidden microscopic energy stored inside the system. That matters because humans are visually terrible at detecting hidden energy. A parked car looks inactive, but gasoline contains chemical energy waiting for ignition. Compressed gas looks harmless, until it converts stored microscopic pressure into explosive force, and suddenly everybody becomes extremely respectful of thermodynamics. Internal energy is the invisible reservoir beneath physical behavior. Now comes the second term, work. In this convention, it represents work done on the system, and this is where thermodynamics becomes strangely intuitive. Work is organized energy transfer. Push a piston downward and compress a gas. You are forcing molecules into smaller space. That mechanical compression increases molecular collisions. More collisions mean higher internal energy. The gas heats up. You have transferred energy through organized mechanical action. That's work. Not work in the emotional sense of answering emails at 2 in the morning while questioning your life decisions. Physical work, force acting through distance. And the key insight is this. Work changes microscopic behavior, even though the input itself looks macroscopic. A giant piston moves only a few centimeters, yet trillions upon trillions of molecules respond instantly. The microscopic world keeps score. Now, the third term, heat. Heat is different. Heat transfer is disorganized energy exchange. When you touch a hot stove, molecules inside the stove collide with molecules in your skin. Faster particles transfer energy to slower particles through random interaction, no piston, no organized motion, just statistical chaos spreading itself around like gossip in a small town. And this distinction between work and heat is absolutely critical because both transfer energy, but they transfer it differently. Work is organized. Heat is chaotic. Imagine a crowd inside a stadium. If everyone marches together in one direction, that resembles work, coordinated, structured motion. If everyone runs randomly after hearing a suspicious noise near the exits, that resembles heat, disordered energy, spreading statistically. Different patterns, same underlying energy, and suddenly the equation becomes beautiful. Internal energy changes because energy enters the system through either organized transfer, work, or disorganized transfer, heat. That's it. That's the core idea that helped launch modern engineering civilization. But the deeper elegance appears once you realize the equation is fundamentally an accounting identity. Nature does not permit free energy. You cannot magically increase internal energy without paying for it somehow. Energy entering a system must come from somewhere. Always compress air quickly inside a bicycle pump, and it becomes warm. Why? Because your mechanical effort increased molecular energy. Heat soup on a stove and molecular motion increases because thermal energy entered the system. Different delivery methods, same accounting rule. And the universe enforces this rule with terrifying consistency. A steam engine works because thermal energy changes internal molecular behavior, creating pressure differences capable of mechanical motion. A refrigerator works by forcing energy relocation using mechanical work. Car engines transform chemical internal energy into pressure, motion, friction, and heat through controlled explosions that engineers politely describe with phrases like combustion cycles because repeated microscopic detonations sounds concerning. During marketing campaigns, everything obeys the accounting, even living organisms. Your body is a thermodynamic machine. Food becomes internal chemical energy. Muscles perform work. Heat escapes continuously. You're essentially a walking energy conversion process attempting to remain structurally organized long enough to pay taxes and occasionally find happiness. Which leads to the truly unsettling implication hidden inside the first law. The universe never forgets where energy went. Not exactly. It may spread out, it may become less useful, it may transform into forms humans struggle to exploit efficiently. But it does not vanish. Reality keeps the receipts. And once humanity discovered that engines, industry, chemistry, and eventually modern physics began aligning under a unified principle, behind all physical change lies conserved energy moving between visible and invisible forms. Once humanity understood that energy obeys accounting rules, civilization changed direction permanently. Because before thermodynamics, heat was treated almost like folklore. Useful folklore, certainly. People knew how to burn fuel, forge metal, boil water, and survive winters, but understanding why energy behaved the way it did that was missing. And without that understanding, engineering was basically controlled trial and error with occasional explosions. After the first law of thermodynamics, everything became calculable. Not perfectly, not instantly. But for the first time, humanity possessed a framework capable of tracking energy as it moved through physical systems. That sounds abstract until you realize modern civilization is essentially an enormous machine for controlling energy transfer. Power plants, vehicles, factories, computers, refrigeration systems, jet engines, entire economies. All of them depend on humanity learning how to manage the relationship between heat, work, and internal energy. Take the steam engine. Before thermodynamics matured, steam engines were inefficient monsters that devoured coal with frightening enthusiasm. Vast amounts of heat simply escaped uselessly into the environment. Engineers improved designs mostly through practical experimentation because the underlying physics remained incomplete. But once energy conservation became formalized, engines stopped being mysterious fireboxes and became solvable systems. Fuel contained chemical internal energy. Combustion released thermal energy. Thermal energy increased molecular motion inside steam. Steam pressure performed mechanical work. Every stage could now be analyzed quantitatively. Civilization suddenly gained the ability to optimize power itself. That transformation reshaped geopolitics. Industrial nations gained enormous advantages in manufacturing, transportation, and warfare. Railroads expanded continents. Steamships altered trade networks. Mechanized production scaled beyond anything previous civilizations could sustain. Coal effectively became compressed industrial momentum. And underneath every factory chimney sat the same invisible bookkeeping law. But thermodynamics didn't stop at steam engines. The equation quietly invaded almost every technological system humans would later build. Internal combustion engines, for example, are controlled energy release machines operating under brutal thermodynamic constraints. Inside a car engine, fuel-air mixtures ignite explosively. Chemical potential energy transforms into high-temperature gases. Expanding gases push pistons, pistons rotate crankshafts, motion emerges from microscopic chaos, which is an astonishing sentence when you think about it carefully. Your car is basically converting organized prehistoric sunlight into controlled mechanical explosions, thousands of times per minute, because fossil fuels are ancient biological energy reserves. Plants captured solar energy millions of years ago. Geological processes compressed that energy underground. Humans extracted it and built civilization-scale energy systems around burning it rapidly. Thermodynamics tracks the entire chain. And then there are refrigerators, which might be one of the greatest psychological scams ever engineered. A refrigerator does not create cold. Cold is not a substance. Instead, refrigerators perform thermodynamic theft. They use mechanical work to move thermal energy from colder regions into warmer surroundings. In other words, your refrigerator continuously spends energy relocating microscopic chaos, that humming sound in your kitchen. That is the sound of physics enforcing accounting rules. Even modern computing suffers under thermodynamics. Every computer processor generates heat because computation involves physical energy transfer. Billions of transistors switching states create microscopic electrical activity, and some of that organized electrical energy inevitably degrades into thermal motion. Which means your laptop overheating during 20 browser tabs and questionable multitasking behavior is not a software issue alone, it is a thermodynamic negotiation with reality. Entire data centers now consume staggering amounts of electricity, partly because removing heat has become a major engineering challenge. Modern civilization increasingly depends on controlling energy density without melting its own infrastructure. And perhaps nowhere is thermodynamics more humbling than inside the human body. Humans are not separate from these laws. We are thermodynamic systems pretending to be philosophical. Food enters the body, carrying chemical energy. Cells process that energy through metabolic reactions. Even thinking consumes energy. Your brain, despite representing only a small fraction of body mass, burns enormous metabolic resources because maintaining organized biological structure is thermodynamically expensive. Life itself is a continuous battle against equilibrium. And the first law governs every second of it, but the ripple effect extends beyond engineering and biology. Thermodynamics also changed philosophy. Before energy conservation, nature often appeared fragmented. Heat, motion, light, chemistry, electricity. These phenomena felt separate, disconnected, almost mystical in their individuality. The first law helped reveal something extraordinary. These were not isolated phenomena, they were transformations. Different expressions of the same underlying conserved quantity. That realization unified physics in profound ways. It suggested the universe possesses deep structural consistency beneath apparent chaos. Reality was not improvising randomly. Physical processes obeyed hidden constraints operating everywhere simultaneously. Stars, engines, storms, animals, everywhere. Energy moves, the accounting remains intact, which leads to a strange realization about civilization itself. Modern society is not fundamentally built from concrete, steel, or silicon. It is built from energy flow management. Cities survive because energy enters continuously. Transportation systems exist because stored energy becomes motion. Agriculture scales because humans manipulate chemical and thermal processes. The global economy is essentially a gigantic thermodynamic network wrapped in politics, finance, and occasional panic. And underneath all of it, the first law remains quietly undefeated. Humanity did not merely discover a physics equation. It discovered one of the operating principles of reality itself. There is something strangely comforting about the first law of thermodynamics and something deeply unsettling. comforting because it tells us the universe is not arbitrary. Beneath all the apparent chaos, collapsing stars, burning forests, boiling oceans, exploding engines, living cells, human civilization, reality still follows consistent rules. Energy moves, transforms, spreads, but it does not simply vanish. The universe keeps track. That idea sounds technical at first, mathematical, mechanical, but the longer you sit with it, the stranger it becomes. Because the first law is not merely about engines or physics laboratories, it is about limits, about consequences, about the impossibility of getting something from nothing. Every transformation has a cost. Every system pays eventually, and humanity keeps rediscovering this lesson in increasingly dramatic ways. Industrial civilization extracted ancient chemical energy from the earth and transformed it into motion, electricity, infrastructure, and global economic expansion. Entire nations rose through mastery of energy conversion. But thermodynamics never promised energy use would be consequence-free. The accounting always balances somewhere. Heat disperses, fuel depletes, systems strain, nothing escapes physical bookkeeping. Which makes the first law oddly philosophical for a scientific equation. It suggests reality itself possesses continuity beneath surface change. A burning log and a living organism appear completely different. One is destruction, one is life. Yet, thermodynamically, both are energy transformations. Your body right now is maintaining organized structure against constant energy loss. You consume food, convert chemical energy into motion and heat, and continuously export disorder into the environment, simply to remain alive. Existence is energetically expensive. Even human ambition obeys thermodynamics. Cities require power. Transportation requires fuel. Technology requires energy transfer. Civilization itself is a gigantic anti-collapse operation fueled by controlled energy flow. And perhaps that is why the first law feels so profound. It stripped away the illusion that physical processes are isolated events. Nothing exists independently. Every action connects to larger energy networks extending through ecosystems, industries, atmospheres, and ultimately stars themselves. Because the energy inside your body was once sunlight. That sunlight came from nuclear fusion inside the sun. The atoms composing your body were forged in ancient stellar explosions long before Earth existed. And now those atoms participate in another temporary arrangement called you, which is simultaneously beautiful and mildly terrifying. But maybe the most extraordinary part of all this is how late humanity arrived at the realization. For thousands of years, humans used fire without understanding energy conservation. We heated metal, cooked food, survived winters, built engines, and launched industrial revolutions while remaining fundamentally confused about what heat even was. Then, suddenly, within a relatively tiny slice of history, humanity uncovered one of the deepest structural principles of reality. Energy changes form, but the total accounting remains intact. That realization unified machines, chemistry, biology, and physics under a shared framework. And it all crystallized into a deceptively simple relationship, a compact statement hiding immense consequences. Internal energy changes because energy enters through work or heat. No magic, no disappearance, no exceptions, just transformation. Which brings us back to a human standing beside a fire tens of thousands of years ago. They could not know they were witnessing molecular energy transfer. They could not know combustion obeyed conservation laws connected to stars, engines, metabolism, and the structure of modern civilization. They only knew the fire gave warmth against the cold. And yet hidden inside those flames was one of the deepest truths humanity would ever discover. The universe remembers where the energy went.